There's not really anything more important in second semester intro physics than four equations that are associated with James Clerk Maxwell. They're called Maxwell's equations. While he made some important contributions, he didn't develop them all. He collected them and found what was missing from Ampere's law. Now, we didn't look at Ampere's law because we really need vector calculus to appreciate it. And Maxwell's equations are they can be written very compactly if you know vector calculus. And of course, we don't expect that in here. But just to see what they look like in this form, I've reproduced them here. And we'll talk about what they mean without we won't talk about what these weird symbols mean. This first one is known as Gauss's law, and all it tells us is if we know the electric field outside of an object, we can find the charge inside it that way. This is something that you may or may not have heard mentioned in the first semester of physics. It tells you that if you know the gravitational field outside of the Earth, for example, you can find the mass inside it. And it's what we use to make finding Earth's gravitational pull on us much, much easier than it would otherwise be. This equation tells us there's no such thing as magnetic monopoles. So you won't ever find a north pole by itself or a south pole by itself. You always find them together. Remember, this one, maybe someday this will be shown to be false, and there will be isolated magnetic charges somewhere. And we know what will have to change. You know, we know how to write the new law if it turns out there are any magnetic charges anywhere. The third one is actually Faraday's law. And what this is telling us is a changing magnetic field gives us an electric field. This part of the fourth equation is Ampere's law that we're familiar with, and it tells us that a current will produce a magnetic field. The part Maxwell added is this. This tells us that a changing E field will also produce a magnetic field. Now, if we had these four equations and we knew vector calc, we would actually be able to combine them and get what are called wave equations. And what they predict is that there are these waves of electric and magnetic fields that can travel through space. And what we'd see is if we have a changing electric field, it gives us a B field, which will also have to change. A changing B field gives us an electric field, which will have to change. We're back over here. So it sort of feeds on itself, and we call it an electromagnetic wave. If we're in a vacuum, we can predict the velocity of that wave using 1 over the square root of these two constants we saw before, permeability and permittivity of free space. This is the speed of light. The exact value for this is 299,792,458 meters per second. This is defined to be an exact value. So if anybody comes up with a slightly better way to measure it, we're not going to add a 0.1 on the end of this. It will actually change the length of the meter. All kinds of light travel at this speed in a vacuum, and that's visible light, the IR from your remote, Wi-Fi, AM radio, FM radio, your cell phone, ultraviolet rays from the sun, X-rays, gamma rays. All these things are connected just like different notes on a piano are related. Now, the way to produce these waves is accelerating charges, and usually at low frequencies we do this by connecting an AC source to a couple of wires. For example, just like this. We stick one wire in each side of a wall outlet. Don't do this, by the way. It would radiate electromagnetic waves because electrons are being first pushed one way and then pulled. And when electrons accelerate, they radiate. The fields that come off of these antennas oscillate perpendicularly to each other as they travel, as shown below here. So we're sending our wave out in the z direction. The magnetic field is waving back and forth, increasing in strength and decreasing in strength in the y direction, and the E field is doing the same thing in the x direction. Now, the formula that connects the strength of the E and B fields is just E equals speed of light times B. We know the speed of light is a huge number, so it may seem like we're saying the E field is gigantic compared to the B field or vice versa. The thing is, we can't directly compare things with different units, so we can't say a meter is large or small compared to a kilogram. The reason we have this large size difference is because of our system of units. In the metric system, 1 unit of magnetic field, 1 Tesla, is a very large magnetic field, but 1 unit of electric field, 1 volt per meter, is tiny. So that's the reason we have this factor that connects the two.